All right, let's get started. Welcome to week 5 of our freshman seminar. We are rocking and rolling. I don't really have much in the way of announcements this week, although as I was prepping the lecture, I remembered that it's not next week, but the week after. I wanted to remind everybody about the job fair that Career Services is hosting. It's taking place in the Rec Center. Next week, I'll make sure that everybody's got some more specific info on timing and whatnot. But I guess my overall point is that if you're interested in going to that and you've got time, you might want to start, breaking out the resume and put the, finishing touches and whatnot in case you want to bring that to the event. Other than that, don't forget we're going to have our same schedule with the quizzes. So there'll be a quiz that opens up either later today or early tomorrow, and that's going to close next Friday at 11 on the content of the lecture today. Sound good? All right. So I'm going to turn it over first to our faculty introduction, and then we'll have our main speaker. So first up, our faculty. This is Dr. James Bryce. He's one of our civil faculty. He's going to tell you a little bit about himself. So with that, let's give him a warm welcome. Here's that.
Mike?
Yeah, let me give that to you.
All right.
I'll get everything pulled up for you.
Appreciate it. Thank you. Dr. Michelson's always much more well-prepared and knows how to use these. So, thank you to your time, really, because when you look at it, you have a much more interesting speaker after me. And I stand up in front of people and talk for a living. It's now what they pay me to do partially. So what we're going to go through today is what I study, what I teach, what my research is. I don't know if Dr. Michelson spent a lot of time talking to you about the life of a faculty member. I don't see why he would, but the life of a faculty member, for what you see, is teaching and grading, and why in the world is he not replying to my emails? From my perspective, it's, hey, I'm teaching and grading, and oh, by the way, I've got this chunk of research that I'm doing. So what is it? Let's pull back the curtain on that. A few notes about myself. So this one, that one. There you are. Appreciate it. So just very quickly about myself. Where did I come from? How did I arrive here at Marshall? I've been here for a little over a year now. I started the beginning of last year, so when many of y'all were seniors in high school. I did pick up the use of the word y'all because I moved to West Virginia. I got that as a Texan as a kid, and I was super excited to have it back in my vocabulary here. In the Midwest, they have a hard time hearing that word without laughing at you. So y'all. Did my PhD down at Virginia Tech. I am a Mizzou graduate. Love the Tigers. Virginia Tech graduate. Spent a year at the University of Nottingham in the UK. I was a Marie Curie research fellow. Everyone, Marie Curie, if you don't know about her, study her. I got to figure the right words to use. She's one of the most awesome scientists ever. And I typically replace the word awesome with a different set of verbs or adjectives there. So. Studied in my undergraduate, graduate, and PhD or postdoc work, transportation. Right? We're all familiar with transportation. We've all been in cars or on roads today. My specialty is, okay, if I look at the entire state of West Virginia, and they want to say, for the next 20 years, what should we budget out, what should we plan, what roads should we fix, how should we basically take these large, multi-billion-dollar budgets and allocate them out over several years. I'm the person that they can come to ask, how should we do that? But transportation engineering, there's a lot more about it, right? And there's a lot of questions that we still have to answer. And so I pose these questions to you because I think it's actually something fun and interesting to think about. We're all familiar with connected and autonomous vehicles, right? We call them driverless cars, self-driving cars, vehicles that communicate with each other. Many of us have driven in cars now with adaptive cruise control, where you're driving down the interstate, you set your cruise control, and you don't rear end anyone, your car automatically slows down or speeds up. Those are coming. But with that, there's a lot of issues in transportation engineering. For example, do we need stoplights anymore? Right? If every vehicle's connected and talking to each other, nobody's going to get into a crash. Right? What do we do with parking garages? If your vehicle can drive itself, you're probably not going to pay $20 to park somewhere. You just say, okay, buy a vehicle, come back and pick me up in 3 hours. There's something called mobility as a service, and that's a big issue that we're studying at the national level right now, where not only do you say, bye-bye car, come pick me up in 3 hours, you say, bye-bye car, go earn some money by driving other people around and then come back and pick me up in 3 hours, right? And when we look at from a civil perspective, civil engineering, we start to ask questions like that. Does Dr. Michelson need to design parking garages anymore? How should we mitigate massive effects of transportation infrastructure on the environment, both locally in terms of acidification, eutrophication, various pollutants going into our beautiful rivers and streams here, but also our social structure? Of course, how do we know what road to fix now versus 5 years versus 10 versus 15 years in the future? Can we use open source data and machine learning? Some of y'all might be very interested in computer science. And one beautiful thing we do in transportation engineering is we basically pull a lot from computer science. So, with that being said, roads fail. We have all experienced it. So it's our job to try to figure out, and it's my job in research and studying and the courses that I teach, to try to better help you all understand how we should manage roads, if you come study with me. My lab is in 2301. Wake 2301, you'll know you're there if you walk in and you see all the 80-inch flat panel TVs. It comes in very handy in March. So my office is inside my lab. Dr. Michelson, I'm sure, has my email address, and he can send it to y'all if you have any additional questions or any questions at all. Do you have any questions?
Anybody have any questions for Dr. Bryce?
Yes. I do. That's actually thank you for asking that question. I hire a lot of undergraduate student researchers, multiple per semester. I value it as an educational resource for the students, but also you help me out. I have a problem right now where Dr. Michelson actually offered to work with me on this, and I haven't gotten back to him yet, but I'll just put it out there. I know. I got a problem right now where I walked into class, and I'm not kidding you. I walk in class. It's a 9 a.m. class, and I hear these words come out of a student's mouth. She says, "Oh, I love statistics, but you know what was even more fun was my differential equations class." Not even kidding you. That came out of her mouth, at which point I stopped and I said, "How much can I pay you to solve this problem for me?" Right, so I do. I typically pay on an hourly basis, and it's a very applied, practical. I've got students right now that are designing an open source app for campus. Hopefully we can deploy it to y'all soon, to where you can start to report problems or issues with the infrastructure, all the way from the walls of your classroom to big cracks in the sidewalk that you trip over, issues like that. So yeah, we do.
And that's just for like junior, senior level, because you did mention differential equations.
No, it's not just for junior, senior level. As a matter of fact, if I had a freshman student that came to me and said, "Listen, I'm very interested in doing research," I think it would be very valuable to have someone over the course of multiple years studying. So no, I don't limit it to, what I limit it to is, are you going to take any sort of initiative and are you going to use it as a learning experience? And I think that most faculty that you talk to here will stipulate, hey, this is an educational experience as much as it is you doing something for me. Now, with that being said, I pay you, and so it'd be like, the expectation is there's something that comes out of it. Great questions. No, I've got a meeting at 12:30 right now with research. We're talking about if we could transform 3rd Avenue here by putting piezoelectric sensors, by putting windmills, how much energy could we feasibly produce? And actually, the preliminary numbers are saying that we could produce much of the energy needed by WAEC. So I'm super excited to get to that research meeting and say, let's write this proposal. But I would be available later in the afternoon, and you know where my office is now, right?
I'll get you his contact.
Anything else? No? Okay. Well, enjoy Mr. Farrell. Nice guy. Very interesting presentation, I'm sure. And thank you again, Dr. Michelson, for giving me the opportunity. And that's the best that Kansas will ever do. I'm sorry, Mizzou grad. Yeah.
I'm going to just go ahead and turn it over to Mr. Farrell. Take it away.
All right. Hello, everybody. How are you? My name is Sean Farrell. I'm from here in Huntington. I'm a professional engineer, mechanical by trade, that works at a company called Service Pump here
down in the west end of town. I'm going to kind of go through some of my experience, what I do, give you guys a quick lesson on pumps, but also talk about the things that I wish I had known when I was your guys' age, when I was a student, a freshman in engineering. So this is me. Was born in Huntington, raised in Huntington, went to high school here. I went away to Purdue University where I got my undergraduate degree in engineering. My degree says Bachelor's of Science in Engineering. My major was interdisciplinary engineering that I'll talk a little bit about here in a second. I later went and got a master's here at Marshall. Spent a lot of evenings after I had my first kid, the second one on the way. So I was driving to Charleston a lot of evenings with a wife with a baby at home and another one on the way in order to get my master's here at Marshall. Then I took the PE exam, which I understand you guys talked about recently, and I'm going to go into a little bit as well in 2011 here in West Virginia. So when I was a junior, I think in college, sophomore, junior in college, I started working as a summer intern at J.H. Fletcher. Some of you may or may not be familiar with it. It's on the east end of town in Altizer. It's an underground mining manufacturing company where they design and build mining equipment for all over the world that goes underground. I ended up being there for about 15 years where I was a project manager for them. Designed equipment, had draftsmen who drew underneath me. And one of the neat things about that job is that I got to draw stuff. I got to take customer input, design a machine to do a specific custom job for them. And then when we draw it, I'd oversee a team who would help me make the drawings. And then we'd build it right there on the same property. And so you kind of, there's some office work, there's some out in the field work where you go out in the shop and you make sure everything fits together like you expect it. Not everything gets built perfectly in the real world. It's not being built inside a computer. It's not a watch. And then, once it would go underground, a lot of times I'd go and meet with the people who actually operate it on a day-to-day basis to figure out, what's working, what's not working, how can we make it better. When it breaks, you got to figure out why and try to understand how to make the piece of equipment better. So I did that for a long time. In 2015, I left. Started working as the principal engineer at Service Pump. My brother Patrick had bought the company the year before and had talked me into leaving what I was comfortable with and joining him. He needed an engineer, so now I do all of our engineering and some design and sales work. I run all of our computer stuff. We've kind of gone through a digital transformation of the company where we went from having a lot of paper and now it's all on the computer and Salesforce. I'm like our Salesforce administrator, do all the quality, all the warranty work, and a lot of the design work and sales work. So I kind of have a lot of hands at Service Pump. So these are the four kind of big things that I like to hit on with a class like you guys. It's the things that I wish I knew when I was sitting here. The first thing is everyone in the room is smart, right? I'm sure a lot of you come from backgrounds where in high school you were probably near the top of your class, a lot of you. Used to making A's, and that's why you're going into a STEM major in college. So I graduated in '99 from Huntington High. There was 511 people in my class. I was fifth, and I got to Purdue, and I was dumb, right? It was not special at all. I was able to coast through high school, show up, get my A, and didn't have to do much. So I was a good kid, stayed out of trouble, showed up, got an A, had a 4.3, move along. You can't do that anymore, right? You guys are essentially adults at this point, right? And you have to be responsible for yourself. A lot of that's going to class. No one's going to make you. And Dr. Michelson would love to see you guys and all your other professors and your time here at Marshall. But the reality of it is that you guys, if you're living here on campus, if you're living away from home for the first time, you're probably drinking a little, playing video games, staying up late, hanging out, have a new set of friends. No one's going to make you come to this room, right? So you guys have to do it yourself. You have to get up and do it. You can't coast. You can't not do the work and show up and make the A that you made in high school because it just doesn't work anymore. I didn't know that at first, right? We played a lot of Mario Kart and everything else. and skipped a lot of classes. I had some lecture halls, some math classes that had 500 people in a lecture hall. And then we go into smaller recitation classes. They don't notice if you're not there, and frankly, they don't care. They're going to get paid regardless. So you have to take the initiative. You have to take ownership of your own education and show up, and be accountable to yourself. The third thing is seek help when needed. Like, you're probably going to get into some classes that you don't understand everything just by doing it once or doing the homework. We talked about differential equations. It's great that Dr. Bryce found someone who said they love differential equations. I wasn't one of them. It wasn't easy for me. Some of it is easy. Some of it's not bad. Right? You guys probably haven't really gotten into that kind of classwork yet, but the basic stuff's easy. They're going to teach you this really long way of doing a differential equations question, and then after you spent 4 weeks learning this really long way, they're going to say, oh, by the way, here's the really simple way of doing it, but you needed to know the theory behind it. And then you're like, well, that kind of sucked, right? Now I could have done this thing that took me a whole page, and now it takes me 30 seconds. But then it gets really hard, right? You start adding in the geometry on top of it, and the definite integrals and third order equations, and that's where I kind of went. So at one point I ended up asking for help. So I knew I wasn't doing well in those math classes, and so I went and got help, and I actually was with a math tutor on September 11th, and didn't understand why the student working the desk was listening to the news on the radio loudly in the library, but because it was September 11th. But the point is recognize within yourself of when you're struggling, when you need help, and be willing to ask it. When I say the professors don't care if you show up or not, they do care. They want you to get a good education, but they can't do it for you. And if you show up in their office hours, you show up asking for help, if there's study sessions, if there's sometimes there's homework sessions, go to their office. You don't understand something, go to their office, be accountable, ask them for help, and when you ask them for help, they're going to know your name. Right? They probably don't know the name of everybody in this room, especially if the rooms get bigger than this. But if you're the one showing up in their office, asking the questions, right, they're going to see the test, see the homework, see your name, and you're probably going to get the benefit of the doubt. Like at this point in this room, this cat right here, Dr. Bryce knows who he is, right? Because he raised his hand, he asked good questions. It's about showing up, engaging, and being noticed. And the last one is consider this your first job interview, like your first real job interview. You're not working at one of the restaurants here or the bar. This is the stuff that you got to do to get the internship, to get the real job, right? Your work ethic at this point, being able to show up, work hard, get a decent grade, like this is your first job interview, and it's going to last, for the next 4 years, maybe a little bit longer. But take it seriously, because it does matter. So this is from the state code. You need to know every single word on here. This is what an engineer means in West Virginia. It's written in state code. It's a protected word. You can't just walk out in the street and say, I'm an engineer, and offer services saying, hey, I'm going to do engineering work for you, even after you graduate. You can have a degree from Marshall that says engineering on it, and it doesn't make you an engineer in the state of West Virginia as a professional. When I was at Purdue, I took a class. We had a freshman engineering. The whole school, everyone did freshman engineering. There was no majors at the freshman level. Everybody did a whole year. And then in your second year is when you decided your discipline. What I decided was a course called Interdisciplinary Engineering. I got to take a lot of different topics and combine them into kind of my own major. The focus that I did was called robotics. It sounded cool. I got to see a lot of different things, but without going into the depth that like a mechanical only would do. And at the time, I didn't realize it, but the way I went about my coursework was not ABET certified. Now you guys are. Is there any major here, any course here that they won't leave with an ABET degree? So you guys are cool here, but like Purdue has 27 different engineering degrees. And I think 2 of them are not ABET accredited because of the way they mix them together, because the student's allowed to essentially choose their path. At 18, I didn't really understand what that meant. In the state of Indiana, it didn't really matter. But in the state of West Virginia, it does. And in most places, it does. So that's a mistake that I made, not knowing that when I graduated Purdue that my degree wasn't going to be ABET certified. You guys don't have that problem again. So the importance of that is that to become an engineer, by the state definition of the word, to be able to offer professional services, to work as a PE, to certify drawings as civil or mechanical, you have to take a couple tests. When you graduate your senior year in the spring, you'll take what's called the FE exam, the Fundamentals of Engineering. It used to be called the EIT. A lot of people still call it the EIT, the Engineering Training. And it's a basic, widespread test that's, I think it's still 8 hours? Is it 6? So it's a 6-hour exam you're going to take in the spring of your senior year. They won't give you the results until after you graduate, but it's the first building block into becoming a professional engineer. So you take that, you pass it, and then you have to work underneath of a professional engineer, underneath their supervision for 4 years, and then you can take the PE. So I didn't really realize how important my degree was until I went to apply to take the PE in West Virginia, and they told me I couldn't. A lot of the reason I went to Marshall and got the master's degree, because they were working on getting, at the time, just a BS in engineering certified by ABET, and because of my master's degree says a master's in engineering has the same title, it gets grouped in with that. And so the reason I was able to sit for the PE in West Virginia is because of my Marshall degree, not because of my Purdue degree. At 18, like I said, at 18, I didn't know. Hopefully you guys aren't going to have that issue, not have that problem. On the right here, these pencils, I think you guys are still at the point where, is anybody born after 2003 or in 2003? Everybody's older than that still, thankfully. I don't feel like I'm that old yet. I am, I guess. So these are the 2 pencils that I took those tests with. I still have them. They're important to me, right? That's how much like these tests mean for your engineering profession to be able to work as a professional in the industry when you're done. My son, my 8-year-old son, calls these lint pencils. He thinks the stuff, the lead inside, he calls them lint. He saw them sitting on the counter this morning and thought he was taking them to school. Like, oh, like this pencil's 16 years old right here. And this one's from 2011 when I took the PE. All right, you walk into those exams, you have to have a calculator and nothing else. Certain calculators are approved. A lot of them aren't. You will leave your phone at the front of the room, probably even out of the room. So you literally walk in with a calculator. If you have a hat on, turn it backwards. No earphones, no phones, no nothing, right? You get a book and a pencil, and they say good luck. So, at the end of the day, these are still important to me, and kind of, I guess, a badge of honor for what you have to go through to pass these things, especially the professional engineering exam. I studied for every waking hour, lunch breaks, before work, after work, till I went to bed, all day Saturday, all day Sunday, for about 100 days ahead of the exam. So, it's a big deal. It's how you become a professional, and it's how you can essentially, go to that next level and do something with the degree that you guys are working towards. So you might ask, like, what should I be doing now? So these are kind of the things that, as a student, progressing through this, working as an intern, maybe getting a summer internship or a winter internship, which, by the way, you should be starting to think about now. You should be targeting companies that you think you want to work for, writing them, and by the end of the year, like in December, if you want to work this summer, you should be thinking about that and having a solid plan in place, probably by January 1. If you wait until May and you go out trying to find something in May, there's probably not going to be a lot of opportunities. So if you're wanting to work this summer in an engineering type internship, start thinking about that kind of stuff now. As a student in groups or in an internship or a job, you need to be a good team member. Don't be the person dragging behind. Show up, do the work, contribute, and work hard. The third thing, a lot of what you're doing is learning how to learn. You're not going to learn, by the time you graduate, you're not going to be able to walk into a job and know how to do it, right? But you're going to know how to figure out how to do it. If I give you a new coding language, or how to calculate, whether this bridge is strong enough, you're not going to know offhand, but you're going to know how to figure it out. So a lot of this process is learning how to learn, learning what questions to ask, learning how to get to the end result that you're looking for, as opposed to just being handed an answer for something. So that's where, it's a foundational thing. It's not going to teach you how to be an engineer. It's going to teach you how to figure out a problem, how to solve it, how to learn it, and then the work experience. Here's a couple pictures, some projects I've done with Service Pump. So we're in the West End. We solve water problems. It's kind of our motto, whether it's wastewater, clean water, or storm water. We fix things, we sell things, we build things, and so we have a fab shop. We repair motors, we build panels, and a machine shop. So this is kind of a combination of all those things where you have to figure out how much stuff weighs, how much buoyancy you have in your floats, do drawings for the walkways and the platforms so that it's big enough, you have enough space for your piping. This is on a lake somewhere, probably on a coal property that has two big pumps sitting out in the middle of the lake where they're pumping water up into the mine. But it combines a lot of those different things of buoyancy and structures and spacing and planning, things like that, as well as the electrical theory that goes behind running this and making sure that it doesn't short out and that you meet all the safety requirements. My favorite color, West Virginia autumn, the leaves. We're getting ready to get into that, so if you're not from the area, enjoy the foliage getting ready to happen. It's another platform that's out in Illinois that we did. This is all drawn in CAD. I prefer Solid Edge because that's what I'm used to. You guys might use AutoWorks or SolidWorks or AutoCAD. This is the program I'm like. This is actually done in AutoCAD, I believe, which is Inventor is what they call it now, right? And so the trick with this platform was it's not on floats, it's on pillars, right? And so you see the green members are I-beam structures with tubing that hold the walkway, and then the silver pieces going through the middle of them are essentially pylons that are going down to the bottom of a lake. So I had to figure out how much all this weighs, how the weight's distributed, how the pylon's going to interact with the ground. You can see there's a slope here going down from the bank to the bottom of it, and then sizing all those feet on the bottom of them so it doesn't sink, right? And to figure out that it didn't sink, I had to figure out how much it weighed, what the bearing pressure was, and how much the soil could take. I had to trust the customer that the soil would take what they said it would take, because we weren't going to go out and test it. And then if they were wrong, I actually have provisions in here on how to adjust this if it does settle after the fact. So this whole thing actually can float up because we didn't secure it in the downward motion. So this whole green thing, we actually could slide up and shim underneath if after a year, 2 years, 5 years, it does settle. We have some ability to help fix the problem afterwards. So it's not only just doing what you're asked to do, but then figuring out what can go wrong, and then fixing what could go wrong, and then fixing that part again, and then doing it a third time, and then something else is probably going to go wrong anyway, so you got to figure it out. But we had a little bit of foresight trying to figure out what the problem was. This is the actual piece under construction, big cranes, things like that, welding it together, being out on the lake while we were doing this. This is a fun project. It's another thing we did where they didn't even have a lake. So we made big cans to put the pumps in, dug a big hole, dropped these big cans, these blue cans down into essentially a hillside, and then used a small creek to flood them. So we kind of created our own pond, tied them together with this manifold down here at the bottom. We got gate valves and check valves to prevent backflow. One of the lessons I learned from this one is that I undersized this manifold down here at the bottom. So the velocity of the water going through the pipe was too fast. And what would happen is if I turned on all three of these pumps, the water being pulled out wasn't being replaced fast enough with the water coming in. We were pulling too much velocity through the pipe, and basically they would fight each other. And you couldn't really predict which one was going to win, but one of them was going to get the water and the rest of them were going to starve. So we ended up having to dig it out, put a bigger pipe in to slow the water down, to flood each of these three wells a little bit faster. Systems also have control valves. You'll notice that if you have a water main break here in town, it's probably going to happen at 2 or 3 in the morning. Right? Saw a complaint on Facebook from someone saying they're jackhammering the street out in the middle of the night. It's 2 a.m. trying to sleep. Why would you do that? The reason is that's when stuff breaks. It was actually the gas company. Can't have a gas leak. They go fix it whenever it happens. The reason things break in the middle of the night is because industry stops using water. The valves close, the water backs up, and when the water backs up, it builds pressure in the pipe. If all the valves are open, it's flowing. Not a lot of pressure, but when you take your thumb and you stick it on top of the hose, what happens? The pressure builds up. That's what happens in the middle of the night. Not as much water is being consumed. Your faucets aren't running. Your toilets aren't flushing. Everyone's sleeping for the most part, unless you're a Marshall freshman down on 4th Avenue. And so that's when stuff breaks, and that's why you'll see it. Pressure reducing valves can help that. You can put timers on them, things like that, to help protect the systems. They're expensive and they're preventative, and a lot of people in government react to things instead of be proactive about them because of funding. They can't afford to do all the kind of work like that up front. This is a pump control panel, sensors, breakers, things like that. Tells it when to turn on, turn off. So we'll go through a quick first pump lesson on how to size a pump. What's a pump do? It lifts water, right? At its basic, it takes water from a lower spot or any kind of liquid or gas and lifts it up. This is an old farm pump. It's got a check valve on the bottom that when the handle pulls up, that check valve lifts and allows water to suck up into the throat, into the column. The blue part is another check valve that's timed on the opposite way. It's hinged the opposite way of the red one. And all it's doing is lifting. It's physically lifting water with the horsepower you're putting in with your arm, right? At its basic, this is what pumps do. They lift water. A lot of different kinds. A lot of them are centrifugal, meaning they spin, just like a hurricane. You see on the Weather Channel, the hurricane, the center is the low pressure spot where all the air gets sucked in. Same thing with the pump. In the middle, it's spinning. It's not turbulent. It's a low pressure. As it spins, it increases the velocity of the water going out to the sides. That velocity is in turn turned into pressure, which allows the water to move faster. When the water's moving faster, Bernoulli's law, it gets to go higher. That's just the way it works. If you're sizing a pump, the first things you want to know is how much water do I want to move and how high do I have to lift it? Those are the two main questions. And all pumps are going to be designed with a pump curve. The bottom is the flow rate. This is going to be how much water is moving, and the head is another word for pressure. This is what's going to be how high can it lift, how much pressure can it make. So if we kind of put in just kind of some numbers and a grid with it, you can see on this pump, the black line is where the pump's actually going to run. The pump doesn't know how much pipe it has. It doesn't know how far, it doesn't know how high. All it knows is how hard is it for me to push against my outlet, right? Do I have a thumb on it? Do I have a stick on it? Do I have nothing on it? Do I have a million miles of pipe? It doesn't know the difference. So when a pump feels this much pressure, this is where it's going to run at. It's going to run that much flow, right? So this one's going to run at 55 feet ahead at 400 gallons. Like I said, feet ahead is a term commonly used for the pressure. It can be converted into PSI. 1 PSI equals 2.31 feet ahead. From a practical standpoint, if you took a colander or a graduated cylinder, and at the bottom of it, if it was 1 square inch of area, and you poured 1 pound of water on it, the pressure would be 1 pound per square inch, 1 PSI. It would physically fill that column 2.31 feet. And so one day I'm going to build one of these because I think it's one of the few examples in life of a real life physical, I can see it conversion factor. But that's what it is. You're used interchangeably. Most people talk in feet. So your head has 2 components. Static head, which means how high am I going to lift it? How high is the mountain I'm trying to lift? And friction head, how hard is it for me to go through the pipe? You have a pipe, it's going through, and the water's grabbing the edge of the pipe. So the faster it goes, the more uniform the water flows through it. The stuff in the middle, nothing's touching it. It's going really fast, so it's going through pretty cleanly. The stuff on the edges is getting held back. It's like rubbing your hands together or dragging your feet on the floor. It goes slower. So this is friction. The other part's static head. How high am I lifting it? Here's our pump. Here's our water feeding our pump. This is how high it's lifting it, right? So those 2 components, static head, how high am I lifting, and friction head, how hard is it for me to pump, or what makes a pump. That's how you calculate your total head. This picture here, there's something wrong with it though. how high does this water have to be lifted to get from this point to this point? Right? It says that this is the static head, right, from here to here. Right? Is that true? You guys, can you figure out what's wrong with the picture? How do I get the water into this tub up here? Yeah, it goes through the pump on the bottom, and then where does it go? Up the pipe, right? How high up that pipe does it have to go to get to right here? Let's go really up there, right? If this pump was just calculated so that all it could do was right here, that water would be stuck in that pipe right there. But I found the picture on the internet, so it has to be true, right? So anyway, this is wrong. This should be drawn up to the bottom of that pipe. That's the static head. That's how high I have to lift in order to actually get the water up in that upper chamber. Friction head has this fancy equation. C is a constant based on the material of your pipe, whether it's plastic or steel, old or new. Q is your flow, D is your diameter. So I'll go through a quick example. If I have 700 gallons clear water, which matters because of the specific gravity of water, through an 8-inch SDR11 pipe, that's the size, that's how the thickness of the wall. The pipe is 10,000 feet. What's the system? So I take these levels. So this is what the inside of an actual 6-inch SDR pipe is. That's the measurement. Here's my 700 gallons. This is the coefficient that comes with that style of pipe. I have 1.871 feet of head per 100 feet, right? Per 100 feet, but I have 10,000 feet. So my friction head for this system, I have to multiply it by 100 to get up to my 10,000 feet. My friction head is 187.1 feet of head. That's the friction head created from this flow through that pipe. And so if my pump was trying to additionally pump that 10,000 feet through that 8-inch pipe, and from where the pump was to the top of the hill that it was pumping up to was 25 feet, my total system head would be 212 feet. Right? I have to take my static head, my friction head, and I have to combine them. I don't do any of that. I made an Excel spreadsheet. I type in 4 numbers, I pick a pipe, and I size it. So this is what you do once you know how to cheat and do all the work so that I don't have to do all that calculations over and over again. But if you don't understand how this stuff works, if you don't understand the equations behind it, the theory behind it, none of it matters. Like you don't just get a book full of Excel sheets in order to be an engineer. You have to actually understand the principles behind it. To calculate that curve, or system curve, what I would do is I'd take that equation and I would go through iterations. I'd start with zero flow. Right? At zero flow, this goes to 0, 0 times 0 is 0, everything's 0. I just have whatever my static head was, which is 20 feet, that mark there. But then if I made this 100 gallons, I'd have a little bit of friction head. So what would happen? It would go up a little bit, right? My 20 feet plus whatever my friction head is for 150 gallons. I'd do it again at 300, 450, and you see these dots become a line. This is what my system's actually going to do. This is what the water flowing through the pipe will actually look like. This black line comes from the manufacturer of the pump. This is the pump curve. This is what the pump's going to operate at whatever pressure. And wherever my system curve intersects with my pump curve, this is what is actually going to happen in the real world. This is where the pump's going to run. This pump's going to produce 475 gallons. It's going to, if I put a pressure gauge on it, it's going to be at 50 feet ahead. Right? And so some customers say, like, hey, I need 400 gallons. Well, you're not going to get it perfect. You have to find what's the best fit. The best fit requires all these pieces coming together at the same time and figuring out where it will actually run at. To do that, you have to run horsepower curves. You have to understand how much horsepower. If I put, this would take us 50 horsepower to run. If I put a 25 horsepower motor on it, it wouldn't work. It would run much, much reduced, a quarter of the flow that we were expecting. So anyway, it's fast version of how like a pump curve works, how a system works, how everything fits together. This right here, how many have seen this thing before? All right, you guys know what this is? All right, it's the memorial fountain. How many have noticed this before down here? All right, this is where the pump is. All right, there's a water pump that runs this thing. They turn off the power to this thing every November 14th, right, for the ceremony. Right, so underneath this, there's pipe work, there's valves, there's controls. This down here is what makes this actually work, right? And so there's decorative things for pumps, but But there's also, pumps for your wastewater, pumps for your clean water. Turn on your faucet, you flush your toilet. Pumps are what make all that stuff actually work. Here's my contact information if you want to send me an email, ask me any questions. This is kind of the earliest stuff at the beginning. Remember, if you guys have any questions, let me know.
Anybody have any questions for John? I got one. Somebody's got it. There we go.
Do you guys do mechanical internships?
We do sometimes. A lot of them, what we're doing, we have a girl who's a grad student from Marshall, and we've hired a lot of Marshall students doing some Salesforce stuff for us right now. But yeah. Anybody else?
Oh, there's got to be another. Oh, we got two.
Do you use CAD?
I do. When I was at Fletcher, I used it every day. I used it every day of my life. I use it a lot less now. I miss it. But yeah, at the end of the day, it's just a bunch of squares and circles put together to make shapes. Like that big machine from the beginning of it is a $700,000 machine. I've done, I don't know, several $100 million worth of equipment, and it's all drawn in CAD. This obviously, so I drew all this. A lot of this was just figuring out the weight. Like I needed to know how much stuff weighed, where the center of gravities were, how to distribute the weight, where to position the green bars, how many do I need, how big do they need to be. I did all the hand calculations to back this up. I come from a family of lawyers, and a lot of times I ask myself, if I get deposed on this is what happens when you get your PE stamp, right? If I'm sitting in front of a lawyer and something fails, and he asks me why I did something, I need to be able to answer that question. That doesn't mean I have to be right? It doesn't mean like, hey, you made a mistake here. Yeah, you're right, I did. But at the end of the day, when you're designing something, or you're designing a parking garage, if it fails and kills somebody, you can go to jail. So you have to understand what it is that you're doing, and more importantly, understand what you don't know. Know when to ask for help, whether it's as a student or professionally. Know where your line is. But yeah, I mean, I like drawing stuff. I don't get to do it as much as I used to. I miss it.
One more back. You're right. Do you have any undergrad or entry-level positions open at all?
Not at the moment. Not at the moment. But yeah, it's something that we look at. And we would post through the engineering department when we did.
That's another reason that if you ever get an email from Lee McDonald, open it and read it. I just had an email sent this morning where there's a company in the area looking for juniors and seniors. So the juniors and seniors all got that from them. And if they didn't open it, then they didn't see a position of it. So when you see an email from her, open it.
Good stuff. The Corps of Engineers is a big one. There's engineering architecture firms, and J.H. Fletcher is a huge supporter of the engineering school, and they're always a good place to go. That's where I started, and it's a phenomenal company.
We're also trying to organize a presentation in the next couple weeks from Special Metals and stuff. That would affect a good bit of people in the room.
Special Metals. I'm part of a group called Leadership West Virginia, where we go around the state. I'm in a class, like this year's class, where we see a lot of different businesses and hear from a lot of different leaders and talks and experiences. We hosted here in Huntington last week, so it's kind of my turn to show off Huntington, which Huntington's doing really well compared to where we were 15 years ago, towards Special Metals. And being an engineer, living in this town for 38 years, it's the first time I've been through their gates. And so Special Metals is pretty protected, pretty quiet about what they do. But if you get a chance to see them or hear from them or talk to them, they got some really cool stuff.
Anything else? We got a little bit of time. Oh, here we go.
Do you guys primarily do like in-state projects?
We do stuff, we feel like our natural trading grounds, basically 100 miles within the Ohio River from Pittsburgh to St. Louis. We have 5 branches in 4 states. Huntington's our main place down here in the West End. But we have a place in Washington, PA. We have a place in the southern West Virginia coal fields, one in eastern Kentucky, and one out in Illinois. basically if it rains and the water goes to the Ohio River, that's kind of where we feel like we fit best.
Any other questions?
All right. Thanks for having me, guys.
First off, again, let's give him another round of applause.
Thank you.
And again, just don't forget, we're going to have the next quiz. It'll open up either later today or early tomorrow, and it'll close next Friday at 11. That's all we got. Y'all have a wonderful weekend.